First question here is, we have 3 light bulbs, one hooked up singly to a battery. The other 2 are in a series configuration. How do you think the brightnesses of these 2 bulbs will compare to each other? The answer here is B. Now, when we talk about brightnesses, you need to think about power, which there's a lot of ways to think about power, but ultimately that's the statement we're making here. Now, on the configuration on the right, the B and C are in series. The equivalent resistance of this circuit is double that of the other one. So you are not going to pull as much power. In this setup here, we have bulb A in contact with bulb B and bulb A is in contact with the battery, and then B and C are now in a parallel configuration. What do you think about the brightnesses now? Let's see what you guys. C's and D's. C's and D's. The answer is D. The answer is actually D. Now, there is a subtlety here, because yeah, they have the same brightnesses. They all have the exact same brightness, but check this out. The current that goes through A is the same current that goes through B and C. That's true. That's what we're saying here. So there's something different here, though. The current that comes out of the battery on the right is twice the amount of current on the battery on the left. But when it reaches the junction, it splits evenly and then becomes the same current as existed with A. So that's something weird, like they're all the same, but not everything is really the same, because this battery must draw out twice as much current to support the 2 in parallel. Now, if you want to look at the math behind this stuff, the 2 light bulbs have, they're in parallel, so they have an overall resistance of 1/2 R, whatever R is. So having 1/2 R as your overall equivalent resistance will mean that the battery can drive out twice as much current. It goes through, hits the junction, then it splits. And guess what? If we were to add a third battery, a D, then what would happen is 3 times as much current comes out, but then it splits 3 ways, and everything's the same brightness. So that's a neat little trick. Neat little trick, but there's something subtle there. The light bulbs are identical. Both are glowing. What happens when the switch is closed? What happens when the switch is closed? Yes, in parallel configurations, your overall equivalent resistance is less than any of the individual resistors. That's sort of a mathematical rule when you add inverses and you take the inverse. So yeah. Anyway, what do you think here? What happens when you close this switch? What's going to happen to these bulbs here? So I'm not going to tell you anything yet. Let me describe some things for you here. Actually, don't put any more letters in. Okay, because I saw A's and C's and D's and B's and dot this and okay, so I'm going to explain this a little bit, then revote. And please be normal. A, B, C, or D. All right, can we do this? All right, thank you. So right now, with the switch open, when the switch is open, it's like there's nothing there. It's like there's nothing there. So what are we dealing with? We're dealing with a series configuration of A and B together. When the switch is closed, now things go through A, but then there's a junction. So the current has the ability to split here. And so you want to consider what the resistance might be. Answer is D. D. This is an example of a short circuit. Now, these are ideal wires. So there's effectively no resistance down this path. And so if the current's going to decide, am I going to go down this way, where I got this big bully of a bulb in my way, or am I going to take this shortcut here and get back to my house? Well, They're taking the shortcut. Now, the way this normally works is the current splits proportionally according to the effective resistances down the line. But there's no resistance on this branch here. This is what's known as a short circuit. All of the current will go down this branch, and none will go through B. B goes out. Now, A gets brighter. Why does A get brighter? Because the effective resistance of the entire circuit has now been reduced by a factor of 2. B is not connected, so B is not part of the configuration anymore. Okay, having a short circuit here breaks some rules in a way, because this kind of breaks a premise of our problems. If there's a short circuit, well, everything outside of that short circuit's not doing anything. It's ignored. That's the idea behind that. What does this voltmeter read? I'm like, I saw all these C's. I'm like, okay, I'm going to assume that it's really easy. And I didn't even look at my own problem here. Now the answer is great. Now, this is the voltmeter. We talked a little bit about voltmeters in the last class. In fact, the lab they were supposed to on Friday involved a little bit of voltmeters. We're going to do that lab this week. But the idea is that the voltmeter, when you put it on two ends here, you're reading the voltage across this element. Now, this is the only element in the circuit, so it's going to read 6 volts across. Now, the current's 2. The current's 2, but voltmeters aren't reading current, right? They're just reading the potential drop here. Now, the idea with the voltmeter is that it has an effectively extremely high resistance, so that no current is going to be drawn along this path here. It's not a short, it's an extremely large resistance. So basically no current is drawn along this path here, and it doesn't affect the overall behavior of the circuit. The circuit is still providing 6 volts. 6 volts are across the resistor here. The current is 2 amps. What does the ammeter read here? What does the ammeter read here? Same circuit, placing the voltmeter with an ammeter. What's going to happen here? The answer is D, nothing, because this meter will fry. Why? Well, think about this. Now, let me talk about what ammeters are again. Ammeters read current, right? But they need to be hooked up in series with an element, because the idea is that the current's going to go through the 3 ohm resistor, and it also goes through the ammeter. And the ammeter has an effectively 0 resistance to it, so that it doesn't affect the behavior of the circuit. Well, an element that has basically 0 resistance is going to have current driven through it. This is like a short circuit. This is a short circuit. And when I say fry the meter, I mean, it probably has hopefully it has a fuse. And the fuse gets busted, you just replace the fuse. But if you don't have something like that, you could drive a ton of current through here, and it could be very harmful for these stuff. It depends on how these are hooked up. Ammeters need to be hooked up in a series configuration. Okay, now if I hooked up my ammeter like this, it reads nothing. The fuse blows or some other safety mechanism prevents it. I'm not sure what those other safety mechanisms are. They're a little too fancy, I think. I'm not really aware what they are. But if we hook this up and this ammeter here was instead in a series configuration, then everything would be fine. So yeah, 2 amps were running through here until we hooked up our ammeter and created a short circuit. So subtle details about ammeters and voltmeters. They're important points, so just to know what they are and how they're used. We will be using an ammeter and a voltmeter in our lab. And so when you hook those up, well, if you don't hook them up right, your circuit's not going to make any sense. And you'll see that when we do it. All right. We are spending a lot of time today solving circuits. Okay, solving circuits. We have 2 main techniques to solve our circuits. One is to treat it as a combination of resistors, reduce the resistance down, figure out the current driving out of the battery, then go back to the original circuit and see how things split up. That's one way to do it. The other way to do it is to use loop law. Now you can see in this problem here, got quite a number of loops. There are 6 loops in this particular problem here. We could have 6 equations, some of which are redundant, so that would not be the wisest idea. Now, how should you choose your method? What's one, well, how are you going to make sure one is right over the other? Well, here are some considerations to make. These are not always going to work, but this is, 90% of the time, maybe even higher than 90% of the time. These techniques and how you know to use these techniques will work out for you. Okay, what about the other 10%? You just need 90 for an A, right? So don't sweat it. Unless, of course, you got to get everything right and other stuff. But generally speaking, though, if you have a single battery, you're going to want to do the combo resistors because you can easily see how the resistors are going to combine together to form a single one. I could do loop law here, but it's a lot of work, honestly. It's going to be a lot of work if I use loop law here. So I'm not going to opt for that one. So you could do loop law, but I'm going to recommend loop law when you have multiple batteries. That's a good idea. Or just really any time you're just not clear about how the combination looks. Because sometimes things may look very complicated and it won't be clear. Like, I don't know exactly if things are in series or parallel. I'm not sure. Well, then just stick with loop law. You may be doing extra work, like extra math. But if you get it right, you get it right, That's the thing. So I am going to do this as a combination of resistors. And I'm going to do this in a rather clever way. Okay, now you don't have to do it the way I'm going to show you the straightforward method, then I'm going to show you a more clever method. And this is all still utilizes the same ideas. All right, so I'm going to take my original circuit and I'm going to start to name things. Now, why did I name these things the way I did? R1, R4, and R3. I don't know what the heck that's all about, but I guess it's because of the way I name my currents. Current, I0, that's what comes out of the battery. That splits at this junction into 1 and 2. It then splits into 3 and 4. Number 2 does, into 3 and 4. So that means going through these. That's why I labeled them 1, 4, and 3, because of the way I labeled my currents. The equivalent resistance of this group is a pleasant 120 over 53 ohms. So 1/15 plus 1/4 plus 1/8. I flipped it. I left it as a fraction. I recommend you do that just because writing out a bunch of decimals, just, I don't like it. If I got my equivalent resistance, then I can, solve for the initial current that runs out of here. So the initial current that runs out of here is going to be given by Ohm's law, 9 volts over the equivalent resistance, which comes out to a 3.75 amps. It comes out to be precisely that. I'm not going to worry about sig figs for this problem here. Okay, so that's the answer. Now, because these are in a parallel configuration, they all have the same potential drop across them. It's all 9. So what I could do then is I can go over here and just fill out the voltage over the resistance of each one. Now you look at this and say, okay, 9 over 15, fine. Right? 9 volts, 15 ohms, right? 0.6, right? 2.25, right? 1.25, that's the 3, okay? Well, you go back and say, well, why'd you even do this part? Why'd you even figure out the current coming out of the battery? Well, I recommend it because when you add up all these currents here, right, they all have to equal the current that's coming out of the battery. And it's just a nice way to check your work. That's all. You didn't have to do this part down here. You didn't even have to figure out the equivalent resistance. But I did because I want to verify that my answer at the end is right. Now, of course, you could have screwed up any of those steps, and then, well, you just screwed up. So, but that's really the way you'd want to go about doing this here. Now, notice something interesting about these currents here. Now, if you look at the 8 and the 4, right? The 4 ohm resistor has twice the current of the 8 ohm resistor. Twice the current. There's a reason for that, okay? Having half the resistance will impart double the current from another element. Let's go over to the 15. Now the 15, that's almost a 16. It's not quite, but it's almost a 16. That would have made the problem a little bit nicer, honestly, mathematically, but whatever. If that was a 16, that means the current running through here should be about a quarter of what it is through the 4th. And if you look, yeah, it's close to a quarter. It's not exactly, but it's pretty darn close to that. Likewise, there should be a bigger difference between the 8 and the 15. This is about half, right? Okay, so this is just a sanity check. All right, so here's another problem we got here. We got a circuit with 3 resistors here, 2 batteries. We have an ammeter placed in here. Now, what's the purpose of this ammeter? It's just to provide you with some information. It does not get involved in any of the circuit analysis. It's just a label that says, in this branch, there are 3 amps. You don't do anything with this in your equations. I mean, obviously, when you put your current in, you're going to put in a 3, right? Now, here's an example of where doing things as a combo of resistors is not really going to work for you. Because you look at the 3 ohms, and you're like, okay, 3 ohms. But then you look at the 4 and the 2, and you think, well, is that parallel? I mean, it's just not even clear what the combination is here. Because in one sense, I can split at the junction up here, and I can go, and I have options, right? I can go through the 4, and I can go through the 2. Okay, fine, but then both ends come back around to this battery here. So it's not quite the same thing. And then there's a battery in the way. So there's a potential difference happening there. So I'm going to go with it's impossible to do it by a combo of resistors. And I could be wrong about that, but there's no reason to prove me wrong because it's just a dumb idea. Don't do that. If you have more than one battery, we're going to have to go with the loop law. So we have 3 loops here. What do we need to do here? Okay, analyze the circuits. That's kind of vague. Here's what it means. When it says analyze the circuit, you want to know the potential difference across every circuit element, and you want to know the current going through every branch. That's what it means when you say analyze the circuit. What's the potential difference across every circuit element? What's the current in every possible branch? There are 3 currents here. We've already defined I1 to be going to the right on the top. I2 is going to the left. Now we are told that, right? We're told that. So that's not something we will question. We assume that's true. And that makes current 3 very clear. Not only is it 3 amps, but it must go down. Okay, if it does not go down and instead goes up, then we have ripped some kind of hole in the space-time continuum and current is flowing into another universe. And we don't cover that till next week. So for now, we'll just keep it simple. Okay, so if I'm doing loop law, you want to generate, looks like 3 equations. 3 equations. because I have three unknowns, I1, I2, and the EMF of the battery on the right. Three unknowns requires three equations. You want two for loop law, and one that is the junction. So let's look at it. Okay. We know that current 3 goes down. So I can do a junction law statement. I1 plus I2 equals I3. And in particular, the junction that I'm considering is the one up here. However, there's only two junctions in this problem. If I chose the junction at the bottom, I'd still get the exact same thing. So now I want to do my loops. I'm going to do left loop and right loop. I do have the option to do the outer loop, but that's redundant, so I'm not going to do it. For my left loop, I put a little X in the bottom left-hand corner, because that's the corner that I like the best, and I'm going to run through the circuit clockwise. Let's do it. I go up, and I pass through the battery, going with the battery. From negative to positive. That's a positive 9 volts. Bam. I'm going with the current through the 3 ohm resistor. That's a potential drop. Minus 3I1. Then I head down. I'm going also with the current. So a potential drop at this resistor. That's 2 times 3. So I'm using Ohm's law here to figure out what that potential differences there. It's just the current times the resistance. That's a negative 6. And so you can see here, I got my currents. I solve for I1, it's 1 amp, and that means I2 is 2 amps. Still got another loop to do because I still have another variable to go with. I'm going to do my right loop. I'm going to start in the bottom right-hand corner. I'm not doing the bottom left. I don't know what's wrong with me. You could still do the bottom left. I wouldn't change anything, actually. Oh, it's because I'm going counterclockwise. So this bottom right corner is actually like a bottom left corner, right? Because we're going counterclockwise, right? 2 wrongs make a right. That's how it works. So we're going to go up here through this battery from negative to positive. That is a potential gain. I put a plus E here. Current 2 goes, we're going to go with the current through the 4.5 ohm resistor. So that's my current times my resistance. So it's negative 2 times 4.5. And then we head down here, and we're going with the current through the resistor. So that's also a drop, 3 times 2. All right, so again, what I did here is loop law. On the loop on the left, I chose the bottom left-hand corner, and I went clockwise around. You're keeping in mind 2 things. How am I going through batteries? When I go through resistors, am I going with current or against current? Anyway, I solved this equation down here. It looks like the EMF of that battery is 15. 15. Interesting. 15. Okay. So that's actually interesting because could we have predicted how these currents are going to behave? I don't think so. I mean, if you were just given this ahead of time, right? I mean, another problem would be, I'm telling you this is 15 over here, and we'll keep all the currents secret and solve. We could do that. We could do that problem. But it would not be obvious how to guess your currents. I mean, I'm going to guess that there's a current that goes, out of the battery on the right. But depending on what this value of E naught is here, or this value of the EMF, it's possible that this is so powerful that at the junction here, it actually splits and goes out in both directions. That means you're pushing current backwards through the battery, which is okay if it's like a rechargeable battery or whatever, something like that. That's how those work, actually. So, all right, good problem, good application. Is there any questions? Because I'm going to do a lot more examples here, but I did some really fundamental examples of the 2 methods here. Do you have any questions about these things? Okay.
I had a quick question.
Sure.
So the whatchamacallit? The conductivity or what was I again?
The current?
Sorry. Yeah, a current.
Okay.
Yeah. The current before the 2 ohms resistor is the same as the ampere, as the reading on the ampere, right?
Yeah, conservation of current states that through a branch here, this whole branch, because there's no junctions, the current will not change.
All right.
So I could highlight this. I mean color code. Oops. Oh. So if I color code things, here's how it looks. The one amp current exists in the red I'm drawing here. I love this red. This is a great red. This is an exciting red. I don't know. It's almost like an orange. It's so vibrant. The blue will be the current 3, and then let's go with like a pink, right? And that's all what we're calling current 2. So that current is the same throughout on the right and on the left. In the middle, there's a branch there, and it's all the same through those branches. Everything is the same until you reach a junction. Then you have a split, which you may or may not know how that works, depending on how the circuit's set up. So.
All right, thank you.
Yep. Anything else? Let's keep moving here. All right. Now, an important element to our circuits is that a lot of times we want our circuits to be what we call grounded. Yeah. Now, the word grounded's kind of a nice word because, at least traditionally, it absolutely meant that. In fact, most houses that are wired have a ground that shows up in a couple of ways, but ultimately it is connected to the literal ground. So let me go back here and explain something. In this circuit here that we analyzed, we have a 9-volt potential difference. That's a delta V. What we know here is that the bottom portion of the wire here is 9 volts lower than the top portion. So the question I could ask, you is, okay, in this section down here that I'm going to label pink, what's the potential there? What about the part that's up here? These 2 parts here. All I know is that the top part is 9 volts higher than the bottom part. But what is actually the value of the potential? I don't know. You can't know. It's possible that the bottom is at 1 million volts. And above the battery, it's 1,000,009 volts. That's possible. And guess what? The circuit would behave in the exact same manner it does if it was like 0 at the bottom and 9 at the top. There would be no difference because the only thing that matters are the potential differences. That's it. So, however, there are a lot of circumstances where we are going to want to ensure that a particular area of our circuit is at a known potential. And that's one of the major purposes of having a grounded circuit. So there will be an element in your circuit that will be indicated, and I'll show you a symbol for that in a moment here. There will be a symbol in your diagrams that will indicate the area of the circuit that is connected to ground. And that means that area of the circuit is at a potential of 0. The idea behind this is that Earth is connected to a particular part of the circuit. Now, the wires are conductors, and the Earth is a conductor. It is actually a giant conductor. And so when you attach it to the Earth overall has a net charge of 0. So connecting anything to ground will ensure that any excess charge, for example, any potential will bleed off basically and come to a potential zero. Okay. Now, let's just show you some pictures of this. So in this example here, here's our symbol. On the bottom left corner, we have placed our ground element. It's indicated by these 3 dashes that get progressively shorter. Looks a little bit like the battery. It's not the battery though. This is ground. What does this mean? It just means that this entire area that I'm going to currently draw out for you here in pink. Let's do a thicker pink. Let's do a thicker one. Let's do some straight lines, not the squiggly lines. That's not too thick. Whatever, I'll just go with it. Everything I'm drawing in pink here is at a potential of 0. Okay, that's all at a potential 0. Now, you look at this, and then, I remember the first time I saw this stuff, I was like, well, that's stupid. Doesn't all the current just flow out of the wire there? It doesn't. Because there's no potential difference. Current only flows if there is potential difference. When you hook up things to ground, there's no potential difference there. The earth is at 0, and this is at 0, and no current will flow. Unless somehow the earth gets magically charged, and then you got a problem now, but it's not going to happen. So now we know what's happening in this circuit here. We have a 0 at the bottom. We go through our battery. It's a 10-volt gain, and we are actually at 10 volts now. So when we work out the current of this circuit, it ends up being a half of an amp because the overall resistance is 20 here. And so when we come over here, that's 10 volts, and then there's a 4-volt drop across the 8-ohm resistor. So that means we're at 6, and then the rest of it is the remaining 6 volts, and that brings us back down to 0 here. Okay. Now, there's a lot of reasons why you want to do this. There's a lot of reasons why you want to do this. I mean, there's 2 things off the top of my head that I can think of here. Okay. So one is, if you have multiple circuit elements that you need to connect together, say it's one part of a larger, group of electrical components. If you hook things up to each other, you have to really be mindful of the different potentials that exist. For example, since this is grounded down here, it would be wise if I hooked up another circuit somewhere to the ground here, maybe one that had a ground on it. Because here's the thing, if I hook up, say, another circuit that has a potential, say, at 100 volts compared to the one that's here, well, when I hook it up, that automatically creates a 100-volt potential difference, which is likely going to be a short circuit, and it's going to disrupt your circuit and probably drive a lot of current out, and then the current will just eventually flow through the ground until everything's neutralized. So, that's not good. That could be very damaging to the components. Now, the other reason for it is it's a safety mechanism. I mean, your 3-prong outlets in your house are meant for ground. And so the idea is that if something were to happen, say you did have a short circuit or something got damaged or whatever, then the ground is a place for current to potentially flow if there's something wrong with the circuit, if it's not behaving the way it should. So it can be meant as a safety thing as well. So there's a couple reasons for it, among many other reasons, but, safety, 1, 2, to make sure you can properly hook up components. That's why you see a lot of times when you plug in things, a little spark happens. Because when you plug in things, they're supposed to be at a potential difference, and if they do, they're not. Okay, it's like when I go to Winco, and I try to open up the doors of the milk, the freezer doors. Every time I grab those doors, I get a shock. Like, either there's something going on with their doors, like there's some kind of, I don't know, electrical leak or something. Or I just attract a lot of charge. But every time I go to grab that door, I'm always like, I have to hit it with the back of my hand because I don't want to get shocked in my hand. It's annoying. But it's the same thing if you, start dragging your feet on the ground with socks, dragging your feet along, and you go up to your sibling and you touch them on the back of the ear right there and you give them a little shock, that'll piss them off. It's because you've charged yourself and you're not at a potential of 0 and they're probably closer to 0 and you hit and a little current flows. So that's all fun things to do. Anyway. So that's why we want to do this, is we want to just ensure that a certain part of the circuit's at 0, just to make sure that when we hook other things up or for safety reasons or whatever. All right. Hi. Uh-oh. Excuse me. Come on. Computer, wake up. Okay, good on time. All right, so now this picture here is the same circuit that I showed you on the previous page. Same circuit. But we hooked up ground to a different location. Ground was now hooked up between the two resistors. How does that change the circuit? It does not. The circuit is identical. The same current flows. The same potential drops exist. The only thing that's really different is that now the bottom is at a -6 volts. The top is now at a 4-volt difference, and the middle here is, of course, at 0. But it will behave completely identically. So maybe I put ground here because I'm going to hook up something to this portion right here, and I want to make sure that stays at ground. All right. Let's do this one here. How much current goes through the 20 ohm resistor? Okay, now there happens to be a ground here, but so what, right? This problem doesn't ask anything about ground, doesn't ask anything about potential. So the fact that there's a ground there doesn't mean anything. You can ignore it. Doesn't do anything. So I want to solve this. How do you do it? Well, there's one battery and a network of resistors. So it sounds like combo resistor. The combo resistor strat might work perfectly fine for this. You can do loop law as well. You can actually mix the two up a little bit, to be honest. Like, for example, I could combine that 20 and 5 together. That's a parallel configuration. If I combine those together, I do believe I get a 4 ohm resistor. And then you got your 4 ohms in series with the other two, the 2 and the 4. And you can do a little loop law for that. I mean, you can actually mix the two up. I don't recommend mixing the two up, by the way. But you could. I mean, that's what the first thing I saw is that. That probably is the fastest thing to do, honestly. But, okay. So, let's solve this one. Wow, this is busy. Okay, so I'm going to do combo resistors here, looks like. So let's do it. I'm going to zoom in a bit because there's a lot going on the slide here. All right, so what do I have here in terms of combo resistors? My first layer of combo is a series configuration. The 4 ohm resistor, the 20 and the 5 in a parallel, and the 2 form a series configuration. One layer down from that is a parallel combo, the 20 and the 5. So what you ought to do here is deal with the parallel combo first. That becomes 4 ohms, and then add up the 3 in series. You get 10 ohms. With a 100 volt battery and a 10 ohm resistance, you're driving 10 amps out of the battery. So, now, this is what I was talking about earlier here. The 10 amps come up, they go through the 2 amp resistor, and then they split. Okay, they split at the junction up here. Now, what you can do for this is you can figure out what is the potential difference across this parallel combo here. And if once you got that, then you just do delta V over R. And then you get your current that goes through each one. Okay, the 10 splits up in some way. And that's a little bit of work. It's not a ton of work. I mean, because, right, what's the equivalent resistance of this? It's 4, right? So if that's 4, then the potential drop across here is going to be 40, right? 40. And so you do 40 over 20 and 40 over 5, and you get your currents. Fine. But here's another way to do it. This is a little quicker if you can pick up on this. Think about these resistors down here. The 5 ohm resistor is 1/4 of the 20 ohm resistor. When you think about these two together, think about it like this. Because the 5 is 1/4 lower, think about this. This is like 5 parts here. You got 4 parts in the 20 ohm, and you got 1 part in the 5. Altogether, there are 5 parts. 4 for the 20, 1 for the 5. So that 4-to-1 ratio there, that has to be the same ratio of currents. More current has to run through the 5, obviously, than the 20. So if I take my current and break it up into 5 parts, that's easy. That's 2 apiece. So 2 will run through the left, and 8 runs through the 5 ohm resistor. 8 over 2 is 4. The ratio of resistances equal the ratio of currents. So if you think about like kind of a weighted junction, I mean that's always what it is. The junction splits according to the relative resistances. So it's kind of like it's like you're weighting the current here. 4 parts go over here to the 5, 1 part over here to the 20. If you take your current and break it up into 5 parts, you get a 2 and an 8. Now, that's something that you can do really quickly in your head if you've gotten that far, and you can kind of see that. That's a proportion that works there. Okay, I look at that, and I immediately see, 4-to-1 ratio, current's 4-to-1 ratio, what's my current? 10, 8 and 2. That's it, and you do it that fast. But that's, I'm just saying, like, that's something to look forward to, I guess. If you're not, if you're not there yet, then we just do the traditional stuff. What is the potential difference across the parallel combo? And then you do Ohm's law. That's how you get the currents there. So interesting problem here. Now I do have a ground here, so I might as well just talk about it. This whole branch at the bottom down here is at 0. Down here at 0 volts. As I go past the 20, remember it was a 40 volt difference there. So when I come up here, this is going to be a gain of 40. So everything up here is at 40 because I'm going against the current. The current really goes down. I'm going against it. And then when I go across the 2, that's a 20 volt difference, and I'm also going against the current. So 60 is all up here. And then the bottom right corner, negative 40. Right? Because if we're up here at 60, it's a 100 volt battery, then down here needs to be 100 lower. 100 lower would be 40. Now, just to wrap it all up and make sure we got this right, what's going on with the 4 ohm resistor? 40 volts. Okay, and we're going against, so it's going to be gain. And we get back to 0. Awesome. Got it. Great problem. All right, let's just get to this next problem here. How much current goes through each branch of the circuit? Okay, 3 batteries, 3 resistors. You're not doing combo here. You're not doing combo resistors here. This is perfect for loop law. All right, I'm not going to keep you in suspense anymore. Let's jump right into this one. It's a good one. Okay. Now, I don't know how the current's going to go here. I have no idea. I'm going to make a guess. I'm going to say that There's a current. Now, here's my educated guess. The biggest battery is 12 volts. The biggest battery is 12 volts. And I'm guessing that current is going to be coming out of that battery instead of going into that battery. So I'm going to call I naught what's coming out of the 12 volt here. And I'll highlight this stuff so you can see how this looks. But let's draw lines here. So all of the stuff here is my I naught. All that in pink. And then for blue, so I naught. There we go. And then let's do a little blue here, my I2. I think it goes down. I could be wrong about that. I really could be wrong about that. But this is all I2. And then my I1, go with a nice grass green here. Nice color combos. Reminds you a little too much of Easter, which I don't like because Easter is light and pleasant, bunnies and candy, and our world does not like that anymore. So we need to stop thinking about that. So here's our colorful circuit here, how the elements look. Now, this is my guess on how the currents are going to go. I don't know if I'm right, but guess what? When I solve my system here, if I get a negative answer for something, then I just make a little note. I got it wrong. And I just make a note, well, okay, actually goes the other way. I'm going to do a top loop and a bottom loop and a junction law. My junction law is given right down here. I'm considering the junction that's on the left-hand side. What goes in is I naught. What comes out is I1 and I2. That's equation number 1. Now, for the top loop, I've decided that I'm going to choose the area between the battery and the 5 ohm resistor. I didn't have to choose that. I don't really want to choose a junction. It's just strange to me. And I kind of always like to choose a point that's directly behind the battery. It just feels nice. Just, I don't know, feels nice. It's just a preference. You can do whatever you want. You choose any location you like. We're going through the battery, negative to positive. It's a gain of 12 volts. We're going what, counterclockwise here? Okay, so we're going to head to the left. We're going down. And now we're going to the right. We're going to pass through this resistor going with the current. That's a potential drop. Minus I1 times 10. We go through the battery, negative to positive, positive 3 volt gain. Then we take a left, we go up, now we go through the 5 ohm resistor. We are going with the current, that's a potential drop, negative 5 I naught. That's my loop law equation for the upper loop. Let's do bottom loop. I decided to also go counterclockwise. I also decided to start behind the battery, the 9 volt battery. So I go to the right here. I go from negative to positive, plus 9 volts. I then take a left and I go up, get to the junction, take a left. I go backwards through the battery now. I'm going backwards through this battery. That's a negative 3 now. I'm going against the current through the 10 ohm resistor. That's a potential gain. So that's a positive I1 times 10. And then I take a left here and I go back down. I get to my 5 ohm resistor on the bottom. I'm going with the current here, so it is a potential drop. I2 times 5. Now I have 3 equations. I've boxed my 3 equations. 3 equations, 3 unknowns. You do your math magic. However you do that magic, you do that. And we end up with the following answers. Now I think I did choose the correct directions here. I think I chose the correct directions. According to my notes here, I'm not going to, you guys can solve systems of equations. I'm not going to go through the details of solving a linear system with you. Although, if you would like me, office hours or after class to explain a little bit about this, I am more than happy to do that. Absolutely, absolutely. But I generally don't do that. But this is my, there's strange currents. They come out to be strange numbers here, and none of them appeared to come out negative. If anything did come out negative, you just need to make a little note. Current 2 goes the other way then, or something like that. Because the other option here probably would be if I naught's coming in like this. The other option would be that I1 comes in instead of going out. That's possible. It's possible that, because the 9-volt battery is pretty big compared to the 3, it's possible that the current would have been driven to the left and not to the right. So that would have been another valid, I think a decent guess. I1, I0 down, I1 left, I2 down. But you would have got I1 as negative. In fact, it might be interesting. This is a great, you want to study something? Redo this problem and make I1 go to the left. You'll get a different equation for both loops. They're going to be different equations. I mean, a little different because what? You're now going up here, the 10 ohm resistor will be a plus here, and then the one down here will be a negative. But that will be enough. Oh, and then of course the junction law is different then too, right? Because it'll be I0 plus I1, and solve it. And you should get the same numbers, but you got I1 as negative. I highly recommend that. Make I1 go to the left. You get your system, you get the same numbers, but you'll get I1 as negative. Give yourself a big pat in the back for a job well done. That's a great problem to do. It's good to study. Good to study. Good, good, good. Very good. Extremely good. Let me screen share this. This may take me 5 minutes to figure out the screen share, so I don't know if I'll have time now, but all right, I got it. All right, so check it out up here. Ooh, this is a good one. 2 batteries. You want to do loop law here. And how many branches do we have here? We have 3 branches. 3 different currents here. This one's not obvious. It's not obvious which way the current goes here, so this is a good one. Number 2, excellent problem. Single battery and a combo of resistors. The combo looks a little funny, but don't do loop law on this one. Or do loop law because, everybody's just in their houses and we're not even doing anything. And it's not like there's a Dodger game tonight or anything. And you don't just do these problems. And try doing this with a loop law. And don't send me your psychiatry bill after you're done. Number 3 looks like number 1. It is. Number 3 is number 1. But now I'm asking you to identify where all the potentials are located. Okay. And then number 4 is very good problem. Very good problem. It just goes over the basics of how you would you would charge a battery, a dead battery. And so they ask you to actually look at, now this is a circuit as when you hook it up to, a car that's giving you a jump. But a lot of the questions to start off with say, well, what if you didn't have the starter motor there? Or what if you didn't have the dead battery there? You look at different pieces and then you combine together. But these are all very, very good problems. These are excellent problems. Take this one real seriously. It's due on the day of the test. Okay?